In this video, I'm going to spend some time talking about the postsynaptic receptors. One phrase, mantra, that I want you to just remember is that receptors confer biological specificity. And what I mean by that is the effect that any neurotransmitter, any neuropeptide has depends on what the receptor does. If there's no receptor, there'll be no effect of the chemical. If the receptor is stimulatory, it'll excite the cell. If the receptor is inhibitory, it'll inhibit the cell. Okay? So for example, dopamine sometimes is excitatory, sometimes it's inhibitory. Dopamine is always the same chemical. What determines the effect dopamine has is which receptor the cell has. So that's what I mean by receptors confer biological specificity. Now, when we talk about receptors, we divide them into two broad classes depending on what they do. We'll talk about ionotropic and metabotropic receptors. Ionotropic receptors are going to be ion channels. So these are going to be actual tunnels. So when the neurotransmitter binds, ions flow through the receptor. They have to go through the receptor. Metabotropics receptors alter the cell's biochemistry. So they are not ion channels, but they change the cell's biochemistry, and that's how they mediate an effect. I'll show you what these mean in a little more detail coming up. When we talk about ionotropic receptors, okay, we've got ions in the extracellular fluid, for example, here. We've got a spot on the receptor. Remember, the receptor is a gigantic protein. When my neurotransmitter or ligand binds to it, it's going to take the receptor from the closed state to the open state. When the change in shape occurs, now ions can move in, flow across the membrane, where they'll have an effect on the electrical potential, affect the membrane potential, B sub M. Okay? Now, what that effect will be depends on the ions. What if these are sodium ions? When sodium comes in, I'm adding positive charges to the inside of the cell. That's going to be depolarizing or excitatory. What if these are chloride ions, Cl minus? Now, negative ions are coming in. We're adding negative ions, hyperpolarization. That'll be inhibitory. Okay. So, again, this is part of the receptor conferring biological specificity. Right? What this neurotransmitter does here depends on whether this is, say, a sodium channel or a chloride channel. All right. But the one thing all ion channels have in common is when neurotransmitter binds, ions flow through them. They go right through the protein. Receptors, metabotropic receptors, on the other hand, alter the cell's biochemistry when they're activated. Okay, so my neurotransmitter binds. It changes the shape, and it's going to activate some enzymes, some proteins. This will affect the function of other proteins, which will then affect other proteins. Sometimes these will then open ion channels. Sometimes they'll affect gene expression. They can do lots of different things. Okay, but if you look, even though an ion channel may open, right, this itself, this receptor, is not an ion channel. No ions pass through it. This particular one is going to use a set of proteins called G proteins. I want you to remember G protein coupled receptors. If you want to be cool, you call them GPCRs, G protein coupled receptors. This is a really important family. Dopamine receptors, serotonin receptors, okay, lots of different receptors we're going to come across are GPCRs. If something is a GPCR, what you can tell me about it is that when ligand binds to it, G proteins are activated. Those activated G proteins are then going to go affect other biochemical reactions and have an effect in the postsynaptic cell. Okay, so in a general sense, that's what an ion channel, an ionotropic receptor, and a GPCR, a metabotropic receptor, are. Now, ionotropic receptors, again, the key being when neurotransmitter binds to it, it's going to open the channel up. Okay, so we're going to go from a small pore that these big fat ions can't fit through. Neurotransmitter is going to bind to it and it changes the shape. What it does is opens that central pore open, makes it bigger, so now my ions can flow through. Okay, that's in general what an ion channel is, what an ionotropic receptor does. Now, I've mentioned several times that this is ligand gated. Remember, gating refers to what opens it. So in this case, chemical binding to it opens it. That's what ligand gated means. Right, here's an example of the nicotinic acetylcholine receptor. The nicotinic acetylcholine receptor is going to be an ionotropic receptor. When no acetylcholine is around, you can see this inner portion is this size. Okay, it's relatively small. When acetylcholine binds to it, now look how big that pore is. It gets much bigger. Okay, so ions cannot flow through this. Cannot. They cannot flow through. Here, ions can flow. They can go through here. Okay. Now, as it points out, this is a sodium channel. So sodium can't flow in. Acetylcholine binds, opens that up. Now sodium can fit. That's the basics of ionotropic receptors. Now, what the effect in the cell is depends. Everything we have here are ionotropic receptors, okay? Because when neurotransmitter binds, the ion channel opens and ions can flow. In the case of the sodium channels, sodium flows in. That sodium flowing in causes a depolarization. If a little bit of sodium flows in, we get a small excitation. If a lot of sodium flows in, we get a big, okay? That's a graded potential. EPSP, excitatory postsynaptic potential. You can see why I just call it an EPSP. Okay, so our excitatory postsynaptic potential. If this is a potassium channel, potassium's going to flow down its concentration gradient. So potassium's going to go out of the cell. As potassium leaves, right, it's taking positive charges with it. That leads to a hyperpolarization, or an IPSP, an inhibitory postsynaptic potential. Over here we have a chloride channel. So now chloride ions flow into the cell. When that flows in, again, hyperpolarization. Now calcium, there are also calcium channels. Calcium does a little bit different thing. Ca+2, when calcium comes in, it's going to immediately bind to other proteins. When it does that, it loses its charge. Okay, so calcium coming into the cell is not going to act much like these other ions do. The membrane potential isn't going to change. But what does happen is we activate enzymes. Okay, so calcium comes in, binds to enzymes, loses its charge, and then causes other cellular effects. Okay? But this is still, even though I'm acting on enzymes and things like a GPCR does, this is still an ionotropic channel because calcium flows through the channel itself. Now I want to do a quick terminology here. If I have a drug that binds to the same place on the receptor as my neurotransmitter and it stimulates, so drug binds same place as neurotransmitter, and it activates the receptor, it's called a direct agonist. Agonist equals activates, direct equals competes for ligand binding spot. Okay. Now, an antagonist is going to bind, but it keeps the neurotransmitter from doing its job. So it blocks the neurotransmitter's effect. So in this case, my drug is going to bind to the same place where my neurotransmitter would bind, but it doesn't open it up. Okay, that's going to make it an antagonist. An indirect agonist is going to bind to a different spot and activate it. Okay, so here's the spot where the neurotransmitter normally binds. Neurotransmitter binds, sure, and opens it up. There'll also be a place, though, on this receptor where my drug can bind. Since it's an agonist, you know it activates the receptor. What makes it indirect is it binds to a different spot. So look at direct agonists and antagonists. Drug or neurotransmitter, only one of them can bind. They're competing for the same spot. Okay, so I've got drug, I've got neurotransmitter, and I've got one parking spot. Here, I've got my neurotransmitter and my drugs, and I've got two parking spots. They can both bind at the same time. Okay? So we have direct, indirect, agonist, and antagonist. Remember, an antagonist prevents the neurotransmitter from having any effect. Just one last cartoon from your book showing you what a metabotropic receptor does. This is a G protein, so you know that this is a GPCR, G protein coupled receptor. Here we are at rest. I've got my membrane. I've got my receptor molecule just hanging out here doing nothing. When neurotransmitter attaches and binds, it changes the shape. When it changes the shape, that's going to release the G protein. This G protein is going to act as a second messenger. This G protein is then going to activate other biochemical reactions, other proteins. Those are called second messengers. Okay? So we release our G protein, it goes and it activates second messengers. Those go on and have effects in the cell. Okay? So it could turn on a gene, it could open or close an ion channel. Okay, so I can't emphasize this enough. even though activation of a GPCR could result in a channel opening. This is a metabotropic receptor, not an ionotropic receptor. The reason it's not an ionotropic receptor is no ions flow through it. Okay? So as we move ahead, we're going to talk about lots and lots of different receptors. You'll get confused, but I'll help you keep them straight. These receptors, again, are all going to do different things. They decide what the effect of the neurotransmitter is. Thank you.